about to embark on a great folly. This will be the first of 4 lectures. I will certainly be dubbed mad. But by the last lecture, I will either have tamed this beast or will have been trampled by it. Consideration of the Recheaters. The Lagrangian must be constructed in such a way as to respect the transformations that we saw. This equation works for planetary orbits that never shift. But here, causes a shift in Mercury's orbit due to the constant gravitational pull of the sun.
Have you solved it, Professor Einstein?
Not quite yet, but the beast is cowering, that's for sure.
Star, more than 3 times the size of our sun, ought to end its life how? With a collapse. The gravitational forces of the entire mass overcoming the electromagnetic forces of individual atoms and so collapsing inwards. If the star is massive enough, it will continue this collapse, creating a black hole, where the warping of space-time is so great that nothing can escape, not even light. It gets smaller. Smaller. The star, in fact, gets denser as atoms, even subatomic particles, get literally crushed into smaller and smaller space. And at its end point, what are we left with? A space-time singularity. Space and time come to a stop.
I wonder what would happen if you applied Penrose's theory about black holes to the entire universe.
If Einstein is right, if general relativity is correct, then the universe is expanding, yes?
Yes.
Okay, so if you reverse time, then the universe is getting smaller.
All right.
So, what if I reverse the process all the way back to see what happened at the beginning of time itself?
At the beginning of time itself?
Yes. So the universe getting smaller and smaller, getting denser and denser, hotter and hotter as we...
You mean wind back the clock?
Yeah, exactly, wind back the clock.
Wind back the clock.
Is that what you're doing? You're winding back the clock?
That is what I'm doing.
Well, keep winding. And you've got quite a long way to go. Keep winding.
I don't want to fall in.
Well, you've got to go back to the beginning of time. You've got a long way to go. Oh, keep winding. Keep winding. Until you get...
A singularity.
space-time singularity. So the universe born from a black hole exploding.
Keep going.
What do you mean keep going? What? Before the universe began?
No. Keep going, develop the mathematics.
The world has become so fragile that we cannot subject the Earth to the tortures we can now inflict upon it. We are actually tampering with the climate of the Earth and with the very atmosphere that we breathe. Not only are we piling in more and more carbon dioxide in the atmosphere, but we are chopping down the forests of the Earth at a great rate. And these problems are life and death problems. They go to the root of the viability of the planet itself, making the Earth a lot less livable. We are facing problems that transcend nations. When we talk about the greenhouse effect, we're talking about something that affects the entire Earth. All human beings are facing the same problems. It is important that the world get together to face the problems which attack us as a unit. The problems with the ocean, with the atmosphere, with the population, with pollution. The only way we can solve a problem is by a human solution. A cooperative solution. There's one thing that is biologically certain about the human species is that it is a human species. One species. Fight? Who is going to lead in the direction? Never can we sit back and wait for miracles to save us. Miracles don't happen. Sweat happens. Efforts happen. Thought happens. And it's up to us to help have all that happen.
Thank you everyone for tuning in today and spending part of your day with us. I am Mark Tian, a high schooler in engineering training, and I currently attend Eleanor Roosevelt High School. Next slide, please. Thank you. Today we'll be having a wonderful seminar hosted by AEC in cooperation with CSAC. AEC, or the All Earth Citizen Foundation, is a nonprofit organization vetted by the United Nations and the Presidential Volunteer Service Award Association. The AEC Foundation's goal is to provide resources to solve critical issues such as environmental pollution, education inequality, and public health, while encouraging members to look outwards into the greater universe. I'd like to introduce Mr. Lee to talk about CSAC.
Hi, everyone. I represent CSAC, the Chinese American Engineers and Scientists Association in Southern California. CSAC organizes technical symposiums, business innovation programs, and STEAM workshops, and we provide scholarships. CSAC is also honored to have many celebrities in science, technology, and art as our members and awardees, including many Nobel laureates. At the beginning of 2023, we launched the STEAM essay contest to all K-12 students. The topic this year is A Ladder to Extraterrestrial Life. So every K-12 student is warmly welcome to participate in our contest. Thanks.
Thank you for a wonderful introduction, Mr. Lee, and I would highly recommend other students to participate in the essay contest. It's a very awesome opportunity. You can earn some money from it. And with introductions of CSAC out of the way, I'd like to introduce our presenter today. He is an individual of many incredible achievements, an individual who works at the world-famous NASA Jet Propulsion Laboratory, an individual who's incredibly generous, forward-thinking, and funny. The one, the only, Dr. Zhang. It is an honor to have you here today, Dr. Zhang, and I hope everyone in the audience listens closely to his wonderfully educational presentation. Thank you.
Okay, thank you very much for the wonderful introduction, and for the both AEC Foundation and CSAC. And today I'm going to talk about storytelling. It's about tales of space and time. And when I prepared this seminar years ago, and I found this is a very difficult and to explain clearly and about space-time without using mathematics, because the deep understanding of space-time, you have to rely on mathematics. However, and if I stick to the mathematics description about the space and time, and many audience will feel bored. Okay, so you get a fewer audience. And but some people ask why you need to using mathematics, to talk about space and time. This is because our universe can be understood by mathematics. Without using mathematics, you don't have quantum mechanics, you don't have general theory of relativities, and essentially difficult to get into the deep secret of the universe. So the scientists working on understanding the universe using mathematics, they find, wow, many things are fantastic. It's almost breathtaking. Okay, so today, and I'm not going to introduce a lot of mathematics, but I'm going to use some of the show some of the equations as well. If you don't understand, you just listen to it. You just try your best to understand. Also, I'm going to include some very interesting videos. Okay, some of the videos may be difficult to understand if you are not physics majors, but I still want to show it because I want you to get a feeling of what is exactly the space and time. Now, to start, to help you understand, I'm going to start to tell the stories about space and time. Okay, so let's begin with, I prepared about 7 or 8 stories. Okay, the first story is time is relative to space. What do you mean time is relative to space? What time is now? Okay, time is now is 5:34. Okay, you see, in order to answer this question, I need to look at the clock. If I don't look at the clock, it's very hard for me to find out whether or not it's 5 o'clock or 5:30 or 6 o'clock. You lost track of time. So time, what exactly the time is, the time actually depends on some motions of the object. The definition of our time is because the Earth rotates 24 hours one cycle. So you divide each day by 24 hours. And also the Earth is orbit the sun 365 days, okay, one cycle. So each day is 24 hours, 365 days is 1 year. So that's our definition of time. Of course, every day there's a daylight and night times. Okay, so you can see something changes. But suppose you are in a closed box, close all the windows, you don't have clock, you forgot about times. Even if you don't have even if you are not in a closed box, you are outside, sometimes you forgot the time without looking at the clock. But sometimes people disagree, say, hey, and even if I'm in a closed box, and I still know the time because I'll feel hungry when the time pass by. Yes, you'll feel hungry because when our biology, our digestive system, and it's developed on the Earth. The rotation of the Earth is 24 hours. Okay. Now, let me go back to the topic. Time is relative to space. What do you mean time relative to space? You see me? Okay, if I stand up, okay, I'm about 5'8". Okay, it's about 76 centimeters. Okay, or 1.76 meters. Now, if I walk, okay, the time needed, I walk past the length of my height is about 1 second. Every second, I walk about 1.76 meters. But yes, I can do that. What is my lifetime? Okay, the average human being's lifetime, let's say 80 years old. Okay, maybe 100 years old. Let's be optimistic, 100 years old. Okay, so in 1 second, I can walk past my height and my lifetime is 100 years old. This is our concept of times. Think about how about galaxies, Milky Way galaxies. Hey, Milky Way galaxy is very big. The light travels from this end of the galaxy to that end of the galaxy is 100,000 years. Okay, 100,000 years. So, but the 100,000 years to galaxy is 1 second. That's why the lifetime of the galaxy is billions of years. Billions of years. Now, let's look at some subatomic particles. It's very, very tiny subatomic particles. It's very small. The subatomic particle moving very fast. The time needed for subatomic particle to travel across its size is a fraction of seconds. Maybe 10 to the minus 6 of seconds. But that fraction of a second to subatomic particle is 1 second. So even the lifetime of subatomic particles is only a few minutes, maybe a few seconds, but to them it's 100 years. Just like to the galaxy, 1 second is 100,000 years, 1 second, but galaxy's lifetime is few billion years, but to galaxy itself is 100 years. So when you think about the time, it's relative to space. Why the galaxies, the stars moving so slowly, changing very slowly? Because the time needed to travel across its size, across the space, to us is very long. Okay, this story seems to be not very interesting. Okay, let's try another interesting story. Hey, how about, okay, where am I here? Okay. So let's try another story. Okay. Jump into a black hole. Okay. Assuming, and Mark, are you still there, Mark? Okay, I'm thinking you're still there.
Yeah,
okay,
I'm still here.
Okay, all right. So you and me are going to do an experiment. Okay. And I'm going to jump into the black holes, and you're watching me. Okay, and I'm observe you. Okay, let's do an experiment. Okay, to
Okay,
see
seems interesting.
what is going to happen. Okay, so if I don't look at you, okay, and I say, hey, bye-bye, Mark. I jump into the black hole, I dead. Seems to be normal. Okay, but if I look at you, something is very strange. If you look at me, you found me is strange. Okay, so I say bye-bye, Mark, bye-bye, Mark, bye-bye, Mark. I'm jump into the black hole. But you find when I fall into the black hole, I'm closer to the black hole, my voice becomes funny and my motion becomes slower. You will find I'm look like this. Bye-bye, Mark, bye-bye, Mark, bye-bye, Mark, bye-bye, Mark. At very close to the black hole, I'm almost freeze. It looks like you cannot see me jump into the black hole until the end of the universe because my time slows down in the strong gravitational field, according to general theory of relativity. However, when I look at you, you say, bye-bye, Jonathan, bye-bye, Jonathan. But I found you very funny. When I'm moving closer to the black hole, I found your motion becomes faster. You say, bye-bye, Jonathan, bye-bye, Jonathan, bye-bye, Jonathan, bye-bye, Jonathan, bye-bye, Jonathan. Looks like crazy. Not only that, you're standing on the earth. I found the people on the earth moving back and forth very, very fast. At very close to the black hole, I found people burst, people die, people burst, people die, people burst, people die, and sounds evolve, earth evolve. The moment I jump into the black hole, I see the end of the universe. Because relative to me, your time is very fast. My time slows down, but your time don't. It seems like I cannot jump into the black hole until the end of the universe. And you cannot see me jump into the universe, the black hole until the end of the universe because my time slows down. Closer to the before, seems my time slows down infinitely. So why is that? Because inside the black hole is another universe. I cannot leave this universe going to another universe until the end of this universe. We are trapped in this universe. Ooh, sounds like a very strange things. Very strange things. Okay, in order to help people to understand this, so let's continue to to another story. Okay. Oh, okay. This is an illustration of the time slows down. Okay, when you're close to the black holes, you see that the clock is almost freeze. It's not mechanically freeze. The time is actually slows down. That is about the story of jump into the black holes. All right, so let's do another story. Faster than light. Travel faster than light. People found seems to be impossible, right? Because my physics teacher told me no object can travel faster than light. But I'm going to tell a story about that. Let's imagine there's a triangle, A, B, and C. A, B, and C. Okay. Now, BC is longer, okay, because BAC is right angle. So there's a sunlight, parallel beam of sunlight traveling down. Okay. Now, I want you to observe the shadow of light or the image of light reaching the ground. You can see when the time passes by, the light travel across this triangle. Okay, light travel across this triangle. So let's calculate. Okay, calculate. Okay, now, and calculate the speed. Okay, now when the light travels from C to B, travels from A to B, the velocity of VAB equal to the length of AB divided by time t, right? That's the light speed, speed of light. Okay, let's look at the image on the ground, travels from C to B. Now, the VBC is the length of BC divided by same time, because when the light from A reach to the B, of course, the image is from C reach to the A. There's a problem because the BC is greater than AB according to the trigonometry. Therefore, velocity BC is greater than velocity AB, the greater than speed of light. Oh my goodness. Something B is greater than speed of light. I should tell you this is normal because this is not the real light or real object travels greater than speed of light. It's only the image of that object travels faster than speed of light. So the shadows, the images can travel greater than speed of light, which is normal. All right, so why I'm telling that story? Because I'm going to explain the expansion of the universe. At the beginning, that's the inflation of the universe. All of a sudden, the universe expanded. That speed of expansion is greater than speed of light. Greater than speed of light. From infinitely small to is big. Why? Why the matters in the universe, in the expansion, Big Bang travels greater than speed of light? Let me explain that. All right. Okay, so, and, okay, and hang on a second. Okay. Did I explain this page? Oh, yes, I explained this page. BC is greater than AB, therefore VBC greater than VAB, greater than C. All right, okay, so now expansion of the universe. Let's assuming there's two universes, two-dimensional universe, okay? One is universe A, is a circle, okay? Another is universe B, it's a flat surface. However, one of the universe is moving closer to the second universe until it collides. Now, the universe A is continue to moving downward. Okay, so it had a compact. Okay, that compact point, compact point is a singularity. Now our universe is expanded, but it's not actually that universe expanded. It's the shadow of the universe. It's the cross-section of the universe expanded. Cross-section of the universe expanded. Okay, so universe A is a sphere, let's say it's a 3D, okay? It crossed another universe, which is universe B, is 2 dimensions, okay? Now the shadow of that universe expanded is 2 dimensions. Now think about that, the higher dimensional universe passing through a lower dimensional universe, you create an expansion, which is expansion of lower dimensional universe. My God, this story is even harder to understand. Okay, so just bear with me. I'm going to tell more stories. After you listen to all those stories, you may get a better understanding of what I'm talking about. However, in order to explain it, I need to use some of the simple equations. If you don't understand, just bear with it. Now, I want you to concentrate. To do that, I'm going to close my videos so you can look at the slides, don't look at me. All right, so I'm going to close my videos. All right. So the fourth story I'm going to talk about is what is the fourth dimension? Fourth dimensional space and time. Now, everybody knows we are living in a 3-dimensional world, okay, space. But I want to talk about the 4-dimensional space and time. So I need to go back to Isaac Newton, okay? Now, in physics, there's a principle of relativity that says in any space, the laws of physics are universally applicable, no matter whether the space is at rest or the space is in motion. Right? If you are stay on the ground, you sit there, the physics is the same. If you're on a bus, the bus is moving, well, the space and so the physics is the same physics. Now, to do this mathematically, you imagine there's two coordinate systems. One is xy, another is x prime, y prime. The x prime, y prime is moving towards the right, let's say, along the x directions at speed v. A moment times t later, the distance is traveled is vt. The velocity times t, that's simple physics. All right, simple physics. Now, this coordinate system is called the coordinate transformation systems. If this coordinate transformation is applied to Newton's law, we find that the Newton's law are still the same. When you are transformed from xy coordinate system, which is still, to the x prime, y prime coordinate system, which is moving, the laws of physics is the same. If you try the equation to plug this transformation system into the laws of into Newton's law, you'll find, hey, the result is the same. This means that Newton's laws have the same form in a moving system as in a stationary system. Therefore, it conforms the principle of relativity. So that's the principle of relativity. Okay. After Newton developed his Newton's laws of physics, there's a very genius physicist, James Maxwell. He developed Maxwell equations. This equation is to use to describe electricity, magnetism, and light. So about 160 years ago, scientists made a series of experimental studies about how the electricity, magnetism, and the light works. And the result, if you summarize the result by James Maxwell, he found there's a set of equations called the Maxwell electromagnetic field equations, which are used to describe the phenomenon and interaction of electric magnetic field and also light. However, it was later discovered something strange, that Maxwell's equation did not follow the principles of relativity. If the coordinate transformation I just talked about was substituted into the Maxwell equations, their forms will no longer remain the same. This means in a moving system, the phenomena of electricity and magnetic fields are different from those at rest. How come? Well, something must be wrong. So under the normal circumstances, when the failure of a physical equation is exposed, the first thing to look at is, well, something wrong. The equation itself may be wrong. That is, these equations must be wrong and need to be changed so that the principle of relativity can be satisfied under the coordinate transformation systems. Otherwise, and so you are still the electricity and so behavior will be different if you are moving a bus. Okay. Now, so the scientists at that time, they're very busy and made various attempts, such as introduce some new terms into the equations, so the changes equations will predict new electric magnetic phenomena. But these are tested by the experiments again. They found those phenomena do not exist at all. So you cannot change the equations. If you change the equations, you predict something, experimental will prove it's wrong. As a result, scientists gradually understood that Maxwell's electric magnetic equations are correct. You cannot change it. And problems must be found elsewhere. All right. Now, to continue the story, there's a Dutch physicist, Lorentz. He discovered something very strange, a very striking thing. That is, he found another transformation. Well, if the coordinate system x prime, y prime is moving, there's another transformation system, like the one at the left. The only thing different is that there's additional factor, which is square root of 1 minus v squared divided by c squared. C squared is speed of light. If you substitute that transformation system into the Maxwell equation, he discovered, oh, the equation keeps the same form, unchanged. Well, something very striking, but why? So this transformation is now the very famous Lorentz transformation systems. So this is the beginning of the special theory of relativity found by Einstein. Einstein noted that one of the conclusions of Maxwell equation is that when there's a disturbances in the electric magnetic field, the light is emitted. Okay, and these electric magnetic waves propagate out equally at the same speed in all directions. The speed is the speed of light. Now, another conclusion of Maxwell equation is that if the disturbances source is moving, the light source is moving, then the emitted light will pass through space at the same speed, which is similar to the case of sound waves. It's similar to the case of sound waves. The speed of sound waves is also independent of the movement of the source of sound. Okay. Now, so in 1905, when Einstein is about 26 years old, he showed, he read a paper, he published a paper, he showed Lorentz transformation can be derived if the speed of light is assumed to be constant in the moving coordinate system. Okay. So, after application of Newton's law with Lorentz transformation in the moving system, the mass is changed. Now, the Lorentz transformation, it works in Maxwell equation. Einstein showed it also works in Newton's law if the mass is changed and in a moving system very slightly. You don't notice at all because the normal speed of the object moving is very slow compared to the speed of light. But if closer to the speed of light, the mass will change fast. Now, in this equation I showed you, m0 represents the rest mass of the body. In this way, the revised Newton's law remains unchanged under Lorentz transformation, and the principle of relativity is satisfied. So this is the famous theory of relativity, famous spatial theory of relativity, Einstein found. Okay, so now if you study physics, this is the mass, okay, we are talking about. This is all there is about the theory of relativities. In fact, this formula is all there is about the theory of relativity. It means if you change Newton's law by introducing the correction factor to the mass, everything is solved. Everything is solved. Is that simple? However, there's something very strange, very surprisingly, because Einstein's spatial theory of relativity brings some very important conclusions. Those conclusions, those predictions have been proved by the experiment, again and again. Up to date, no experiment proved Einstein wrong. This is all correct. One of the conclusions is time dilation. That means if the object is moving, the time slows down. Time slows down. Another is called the length contraction. It means if the object is moving along the direction of the moving, it becomes shorter. Another, of course, is the mass is changing. In moving object, the mass becomes greater. Now, one of the most famous conclusion is the energy of the system is equal to mass of the system times square of the speed of light. Perhaps the most important conclusion is the four-dimensional space and time, which I'm going to talk about this later. Now, about the time dilation, okay, the time slows down. Now, if you are college physics, you study AP physics, and usually, it will illustrate by a clock. Okay, you see at the left, there's a clock. Clock is a light beam moving back and forth. Okay, the source of light bounces back by the mirror. So pop, 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 pop. Okay, this is the clock. Now, suppose if the clock is moving, okay, it's pop, pop. When it bounces back, the clock is already moved. So the length of the light traveled is longer. So the tick, each tick between the duration for each tick becomes longer. If it's still, it's pop, pop. Now, if it's moving, it's pop, pop, something like that. People will disagree. This is a trick. Okay, how about using different clock? Well, in the physics, you can test any clock. The countless experiments have proved that not only this particular type of clock will go slow, but any other clock works by any principle will also slow down. In fact, any method of measuring time gives the same result. Time itself actually slows down. Time itself slows down. Okay, the length contraction, it shows, let's say I have a ball, okay? The velocity of the motion of the ball is still, okay? Then the ball is flat. If it's moving faster and faster and faster and faster, you will see the ball is crashed. People will think, hey, this is just visual. Okay, you feel it crash. Actually, it's not crashed, but it's not. The real object in a moving system is also becomes shorter. This can be proved by the mathematics and also proved by the experiment. Okay, and I forgot to shape the slide. Okay, so the moving object, say there's a ball. The ball at the still is see the ball is flat. Okay, when the ball is moving along the direction of motions, its ball becomes crashed. The faster it travels, it crashes again, crashes again. So this is called a length contraction. The length contraction, people think, oh, maybe it's a trick. Maybe it just, you feel it. It's not crashed. Now, many experiments, all the experiments, prove it's correct. And in fact, and the mathematics, if you work through the mathematics, you'll show it. It is correct. Okay, now the people may not understand again, it's confused. But this is the reason we feel that is because we are living in the three-dimensional space. And the time we consider is half dimension to us because the arrow of time, the time seems to be flow in one direction, not the others. But what do you mean? Fourth dimension. The fourth dimension I'm going to talk about is four-dimensional space and time. Now, in a three-dimensional space, the direction of each coordinate system, X, Y, Z, is perpendicular to each other. at the right angles. Okay, this is what our experience. Now, if we rotate coordinate, another coordinate, x prime, y prime, z prime relative to x, y, z, and let the both systems have the same original point. And then we measure the distance of 2 points, okay, in these two coordinate systems. We will find there's a property, it's called length of the two objects. It's independent of any particular way of measuring it, which is the square of the distance is x squared plus y squared plus z squared, which is equal to x prime squared plus y prime squared plus z prime squared, which is another system. All right. So let's do something. In a similar way, if you consider Lorentz transformation, we can find mathematically the distance between the two four-dimensional space-time point is also independent of measurement, which is the following equation. There's an extra term. Extra term is related to the time. Now, I should say the time we understand is t, but in the four-dimensional space-time actually is c squared times is c times t, which is different for our the fourth dimension is the time times speed of light. That's the fourth dimension. Okay, and I'm going to pause my story because some people already feel bored. Okay, there's a lot of equation. I'm going to show a video. The video is going to tell you what is the time dimension. Let's watch that.
Time. It's unique. It's this wild fourth dimension in nature. This is one dimension, this is one dimension, this is one dimension, and time is the fourth dimension.
It's a vision of space-time as a single thing, as a four-dimensional block in which the past and the future are just like spatial dimensions. They're just like north and south in the equations of physics. And so you can construct a view of the world in which the future is already there. And you can say, and physicists do say something very much like this, that in the fundamental laws of physics, there is no distinction between the past and the future. And so time is just another dimension like space. Again, that is in obvious conflict with our intuitions about the world. We go through the day acting as though the past is over and the future has not yet happened and might happen this way or it might happen that way. We could flip a coin and see. We tend to believe in our gut that the future is not fully determined and therefore is different from the past.
One thing we are absolutely sure of is that the rate of time does change. Time is not just simply a progression, like a river that keeps flowing. It can change depending on how fast you're moving through space. And this is Einstein's special theory of relativity. The idea is that the faster you go, the slower time appears to be moving for you if other observers look at you going by. As you go faster and faster and approach the speed of light, your time slows down more and more. And the amazing thing is that at the speed of light, time does not progress at all. There are more everyday applications to this too. For example, the global positioning satellites that allow you to take your location from your smartphone. Those satellites are going overhead very, very fast. They're going at nearly 20,000 miles an hour. And it turns out that that's fast enough that their time is slowed down. They're actually in a slightly different time frame than we are. And we have to account for that. We have to correct for that mathematically. Otherwise, you would not get the right location. So we know that time slows down. We observe this happening all around us. It was a really hard thing in modern physics about 100 years ago for people to let go of the idea that time just has a rate that it flows, that in fact it can flow at different rates for different observers. Then there's the question of what is time related to space? And you may have heard that Einstein talked about a concept called space-time. He didn't believe that space and time were separate things. We certainly perceive them differently in our human brains. We can move through space, but time always seems to go just at one rate and in one direction. But Einstein thought they were part of a fabric, they were woven together. And one of the ways he illustrated this was that you have to adjust space and time so they always kind of balance out. If I am not moving through space, I'm sitting here still in this chair, then time just seems to go forward at a natural rate. Time just flows. But if I start going faster and faster, my time slows down. So in a sense, I'm moving through space very fast. So I can't move through time as fast as I might have. The two balance each other, space, time. If you move through space very fast, time begins to slow down. Space and time are the same thing all wrapped up together, and it all exists all at once.
Okay, so this is, now in the video it talks about 4-dimensional space and time. Now we living in a 3-dimensional space, but we feel the time. We feel another dimension, which is time. But time, we don't feel it as a dimension. We feel maybe half dimension. So some people say we live in a 3.5 dimension because we feel the time. Now, let's show this figure, and I try to explain the time a little bit. Now, let's say if you're moving in the space, the speed of u is v space. Now, you feel the passage of time. The time flows. The speed of time flows is, let's say, it's v time. Okay? Now, if you are moving very fast, the time slows down. The moving of time slows down. Now, if you are not moving fast, you're moving very slow in space, now the time passes quickly. I shall introduce another concept. How about in the 4th dimension? Let's say in the 3 dimension of space plus 4 dimension of time. Mathematically, we can prove everything is moving at the speed of light. Now, if you're moving in the space faster, you're moving in the time slower. But in the 4th dimension, you're still moving at speed of light. Now, if you're moving in the space is slower, it means you're moving in the time faster. You're still moving at speed of light. Now, I'm going to show a video. Most of the people don't really understand this video. I'm going to show it anyway, because the physics student understand it. That's why, and it's a very important concept. This concept is being proven by the physics. We are all traveling through space-time at the speed of light. Everybody travels in 4th-dimensional space and time at the speed of light.
You probably already know that nothing moves faster than light. But did you know that nothing moves slower than light? Nothing moves faster than light and nothing moves slower than light. We're all moving at light speed. Starting from the same point, Alice and Bob move off at right angles to each other. From Alice's perspective, she's going forwards and Bob is moving off to her right. From Bob's perspective, he is moving forwards and Alice is moving off to his left. So what's going on here? Alice and Bob are recording the same event from different coordinate systems. To transform from Bob's coordinate system to Alice's, we simply need to rotate everything by 90 degrees clockwise. Now Alice and Bob are in a drag race. Alice is moving faster than Bob, so she sees him fall further and further behind. Relative to Alice, Bob is moving backwards, and relative to herself, Alice isn't moving. We can plot their positions as a function of time on a distance time graph. Time increases vertically, and it shows Bob falling increasingly behind Alice over the course of the race. Bob sees Alice moving further and further ahead. From his perspective, their motion looks different. But again, they're describing the same event, and we can move between Alice and Bob's perspective using a coordinate transformation. But it's no longer a simple rotation. We have to use something called a Lorentz transformation. The grid lines that represent equal divisions of time and space from Bob's perspective have been warped. From Alice's perspective, Bob is experiencing time move at a different rate. 2 seconds, according to Bob, looks like 2 and a bit seconds to Alice. This is called time dilation, and it's really only noticeable when two objects are moving at very different speeds. And Alice and Bob are moving at very different speeds. While each division in the time direction represents 1 second, each division in the x direction represents 300 million meters. So if we added light to our list of drag races, its motion is described by 2 lines at 45 degrees to the vertical. Bob is falling behind Alice at almost half the speed of light. When we transform back into Bob's perspective, see that although the path Alice takes through space-time changes, the path that light takes is the same. This shows that light appears to have the same speed, no matter how fast you're moving. It's the foundation of special relativity, and it's the reason we use the Lorentz transformation. There are other paths in space-time that don't change when we move between coordinate systems. This line is called a hyperbola, and although the transformation moves points along the hyperbola, points that begin on the hyperbola stay on the hyperbola. All these points have something in common, but what? Let's go back to our original transformation to find out. What curves remain unchanged by rotation? Circles, of course. All the points that begin on a circle remain on that circle, and all the points on the circle do have a common property. They're all the same distance away from its centre. We use this idea to say that all the points on the hyperbola are the same proper distance away from the origin. How long do Alice and Bob take to reach the same proper distance? Well, we can see from Bob's perspective, after 2 seconds have passed, he will reach the hyperbola. Alice seems to take a bit longer. Yet from Alice's perspective, it also only takes her 2 seconds to reach the hyperbola. So, no matter how fast you're going, it always takes the same time to travel the same proper distance. Everything travels at the same speed. Einstein's theory of special relativity forces us to think of time as an extra dimension that we can travel through in the same way that we can travel through the other 3 dimensions of space. And we have to accept that seconds and meters mean different things to people moving at different speeds. The only thing we can agree on is the proper distance between 2 points. But the proper distance is a measurement of space-time, and so has both spacey and timey qualities. Since speed is distance over time, and in space-time, distance and time are really kind of the same thing, then speed loses its meaning, or it's just equal to 1. What we really have control of is the direction we move through space-time. The less we move through space, the more we move through time. And the more we move through space, the less we move through time. Time appears to slow down for fast-moving objects. This kind of trade-off is obvious when it comes to rotation. The more that Bob appears to be moving ahead, the less he can be moving right. So perhaps it's not so surprising that the Lorentz transformation that we've been using is also called a hyperbolic rotation.
Okay, now this video seems to be a little bit hard to understand to non-physics student. But if you're a physics student, if you love physics, you should watch it again. That's the basic proof concept of why we all travel in the speed of light in 4th dimension. So let's continue to tell another story. What is gravity? Why the moon falls to the earth if the moon is not moving? Okay. Now, in the textbook in the museum, sometimes you see a picture like that. It looks like the space is curved. So this is the curvature of space is gravity. Some teachers like to explain like that, but it's wrong. the reason we have a gravity, the reason the apple fall to the ground, it's not because space is curved, it's space-time is curved. The more importantly is the time is curved. So the gravity essentially actually is curvature of time. Oh my God, what is curvature of time you're talking about? Well, go back to the story. At the beginning, if you're falling into the black hole, your time ceases to be freeze. Why? Because the time is curved. Now, I'm going to introduce another interesting videos, okay, about why the curvature, to explain the gravity is curvature of time.
Space-time is an object with 4 dimensions, 3 dimensions of space, but also 1 dimension of time, which can equally bend and curve. Faithfully rendering a 4-dimensional geometry is strictly impossible, and we therefore have to find a trick. A first idea would be to add small clocks to our diagram at each point of the grid. In this way, the space grid becomes a space-time grid, and we understand that time can flow differently depending on where we are. That being said, adding clocks to our diagram doesn't give us much more intuition, and in particular we still don't really understand what causes objects to fall. If we drop an apple, for example, why does it start to move towards the Earth? To really understand, it is necessary to remove 1 dimension of space to represent the dimension of time. In fact, it is the time component of the curvature which explains gravity. With such a diagram, we see that the apple is always in motion. Even when it has no speed at the start of its fall, the apple is still moving in time. It progresses towards the future. When no force is applied to the apple, the curvature of spacetime will gradually bend its trajectory between a temporal speed towards the future and a spatial speed towards the ground. The apple moves in a straight line, but the curvature of spacetime rotates the orientation of this straight line between time and space. We therefore understand that if the apple falls towards the ground, it is because it started with a speed through time. The curvature of space-time generated by the Earth has merely converted this temporal speed into a spatial speed. Having said that, as human beings, we do not perceive the temporal speed of objects. When an apple is dropped, it appears to us to be motionless. We do not perceive the fact that it has a motion through time. From our point of view, we experience the world instant after instant. And this diagram where objects form tubes over time, world lines, is not very intuitive. Our last step will therefore be to slice this diagram, to cut it up instant by instant, in order to form an animation which includes time. The curvature of the universe, which causes straight lines to dive into the Earth, becomes a movement of contraction. The rate of this contraction is constant and perpetual because the curvature of space-time, which depends only on the mass of the Earth, is always the same.
Okay, so this video explains why gravity is curvature of time. Why the time is curved is because the mass will slow down the time, will curvature of time. That's caused the gravity. Now, people find this may be crazy, but this is from the general theory of relativity. In fact, up to date, all the experiment that proves general theory of relativity is correct. Nobody found any experiment to prove that it's wrong. So we have to accept that. So let's continue something interesting. I'm going to tell another story, which is inside the black hole is another universe. wow, inside black hole is very, very small, very, very small. It's just like a point. Why inside black hole is another universe? The reason you have this question is because we are trapped in a three-dimensional space. Now, let's, I would like to give an example. Let's say there's a one-dimensional space. In the one-dimensional space, there's two friends. One is red, one is blue. The two friends, okay, living in a one-dimensional space. One day they have an argument. After the argument, they hate each other. Then the red friend say, hey, I don't like you. I'm going to go. I'll never come back. So he moves, he travels away. He moves in one of the directions. Okay, he said, I'll never come back. But sometimes later, okay, when he moves, he'll find the blue friend is below. I'm going to go up. But sometimes later he'll find, my God, my blue friend is ahead of me. It's very hard to understand. Then they bounce each other again. Wow, I meet you again. I said I'll never come back. But how did you come in front of me? It's very hard for them to understand. The reason for them to hard to understand is they are living in one-dimensional space. From two-dimensional point of view, it is very easy to understand because the red friend, they travels the entire circle, come back to the same point. All right, let's give another direction. Let's say in a two-dimensional space, okay? Now, two friends say, hey, let's move forward in parallel. Okay, let's move in parallel. So we won't meet each other. However, when they move, they found the distance between them are closer. They eventually bump to each other. Now, for them, a two-dimensional space is very hard to understand, but in a three-dimensional space, it's easy to understand because their two-dimensional space is curved. It's just like the blue and red friend in one-dimensional space is curved. They curve in the higher dimensions. Now, go back to our universe. We live in a three-dimensional space, but our three-dimensional space is curved in the higher dimensions. And it's not easy to understand this if we do not using math, but I'm going to give you the result. One of the results, although it's very hard to prove, is the following videos.
If you want to know what it's like inside a black hole, look around. Our entire universe, to the furthest galaxy, we are told, is no more than a closed electron in a far grander universe we can never see. And that universe is only an elementary particle in another still greater universe, and so on forever. Also, every electron in our universe, it is claimed, is an entire miniature cosmos containing galaxies and stars and life and electrons. Every one of those electrons contains a still smaller universe, an infinite regression, up and down.
Well, okay. From that video, you know one of the probable conclusion is we living in a black hole. Actually, in our universe, inside the black hole is another universe. Not only that, it is possible, although we are not proving it. Maybe it's speculation. Inside every electron is another universe. And every electron in our universe contains galaxies and stars and planets and life. Wow, this sounds to be an answer. This is very hard to understand. Now, the reason it's hard to understand is we are living in a three-dimensional space. Now, people say, how about time? Now, to answer what is time, is related to another question, which is story 7. People ask, hey, our universe created by Big Bang. Now, what happened before the Big Bang. Now, to the physicist, there's one notion is there's no time before the Big Bang. Okay. How about the future? And our future is actually connected to the beginning of time. It's very hard to understand, but let's watch another video. It's by Dr. Roger Penrose, which is Nobel Prize. He won Nobel Prize in physics for his theory.
Roger, the Big Bang has now entered common knowledge as the way the universe began, and everybody always asks, how did the Big Bang begin and what happened before that? And philosophers, theologians, physicists now begin to speculate on it. I really come to you because you have some very unique insights into the Big Bang.
You see, if anybody had asked me what happened before the Big Bang, I would have given the conventional answer, which is the Big Bang was this singular state when all our equations go haywire and time and space, doesn't make any sense. Even the question before doesn't mean anything, you see. So that's the conventional answer. You say, you can't talk about it, it's just a meaningless question.
There is no before.
There is no before. If you like, the physical justification for this is that in the very early universe, the temperature was so high, the energies of particles were so high, that it didn't matter a hoot what their masses were. See, mass is what you use if you want to build a clock. There are two fundamental equations in physics that I'm referring to here. One is the famous Planck law, which tells you energy equals E equals h nu. So the energy is proportional to frequency. The other is the famous, even more famous Einstein equation, E equals mc squared, which tells you that energy is proportional to mass. So if you put those two together, it says mass and frequency are basically the same thing. Right. So that means that there's a clock, which is the frequency, is a measure of mass. Now, if you don't have any mass, or if mass becomes irrelevant, you can't build a clock. So in the early universe, the universe didn't know how to keep time. You see, it just it lost track of how fast things were going, you see. And if you take that seriously, you can imagine going to before it. Now, it's a difficult idea to grasp, but it's mathematical. It makes mathematical sense, but it's hard to sort of think this is real physics, you see. But okay, that's one side of it. Now, the other side is think of the very remote future. What do we expect in the very remote future?
We have the universe expanding.
The universe is expanding.
Without limit.
And it's accelerating in its expansion, which is important for this whole picture. It wouldn't work otherwise. And this is this mysterious thing that people worry about. They call it dark energy. Maybe it's just the Einstein's cosmological constant, which is the way I would look at it. But still, we don't know why it should be there, if you like. So, but in this picture, you need it. So I want to say, what's the remote future in this picture? Well, the universe expands, it exponentially expands. And, okay, there's black holes lying around, which have got lots of mass in them. According to Stephen Hawking, these things will, in a very remote future, the universe will cool down to lower than the temperature of any given black hole, even huge ones which have a very low temperature. And they will evaporate away, get smaller and smaller and smaller, and eventually go off with a pop. That's the pic. Now I'm accepting that. I think that's probably right. Eventually, all the matter in the universe will disappear apart from radiation. Now,
very dispersed.
That's right. There's certain assumptions which go into this, but let's accept that there's nothing left but radiation, very dispersed. Now, how do you talk about the very remote future? In fact, the picture I'm trying to describe is a sort of result of my worrying about how boring the universe is. You see, it's going to get pretty boring, you see. And I can't think of anything more boring than waiting around for a black hole finally to disappear pop. You see, it sounds to me incredibly boring. But then I thought, well, who's there to be bored? Not us, you see. The only things around will be these photons and things, and it's pretty hard to bore a photon. A photon doesn't experience any passage of time. So eternity is no big deal to a photon. It just, whoop, there it is, you see. And how do you talk about infinity in relativity, in Einstein's theory, in Einstein's general relativity, how do you talk about infinity? Well, you'd use the same conformal trick. But now, instead of stretching out, which is what I did for the Big Bang before, I'm squashing it down. So I'm saying that in the remote future, there's nothing left which has any mass. If that's the case, somehow the universe doesn't know how to keep time in the remote future. It doesn't know how big it is, you see. So the universe forgets how big it is, in a sense. And it might as well be a small new universe. So the picture, okay, it's crazy.
I followed everything until that very last step where we have a complete expansion, we have complete dispersion, no mass, photon radiations, and the similarity was that there's no clock.
That's right.
Because you have no mass.
That's right.
And that's the same characteristic of the early universe when it was very small.
Yep.
But you have this very big universe that has no clock. And now how do you get to that small universe that has no clock?
But the point is that it doesn't know the difference between big and small.
Because it has no clock.
It has no clock. You see, okay, you've got the speed of light, which enables you to transform from time to space.
Yes.
But since it's got no clocks, it has no way of measuring distance either. So spatial distance becomes irrelevant, temporal distance becomes irrelevant, or time.
So the universe forgets how big it is.
It forgets how big it is. And so it sort of lost track of that, and it becomes the next Big Bang.
Okay, so let's conclude that. So it says the beginning of the universe is connected to the end of the universe. How that be possible? You think about that the blue friend and red friend, they living each other. They travel farther and further. But because their space is curved, they finally meet each other. The same thing as time. The time flows. Time flows apart. So there's a beginning of time, there's an end of time. But because it's curved space and time, and finally the end beats the beginning. It looks like the birth is connected to the death of the universe. Now, let's moving on to another story in order to help to understand this. Now, besides the Einstein's theory of relativity, there's another very successful physics theory, which is quantum mechanics. Quantum mechanics is proved again and again by many experiments to be correct. But quantum mechanics gives an indication our universe may not be the only universe. There are some other universes, especially something called parallel universes. So what is the parallel universes? It has to start with a Schrödinger cat experiment. That is to say, imagine in a closed box, there's a live cat and a radium stone and a bottle of poison. Now, the experiment is set up like that. If the radium decays, the bottle will be broken, okay, and the cat will be poisoned to death. If the radium does not decay, well, the cat survives. But whether or not the radium is decay or not, well, according to the quantum mechanics, because radioactive radium exists in the superposition of two states of decay and no decay. Okay, this is proven to be true. The superposition, okay, is an important concept of quantum mechanics. So that the cat can be in the superposition state of dead cat and live cat. Now, this dead and alive cat is so-called Schrödinger cat. In common sense, there can be no cat that are both dead and alive. One of these two results must occur in the box. You're either alive or dead, right? According to the common knowledge. But the outside observer can only know the result inside the box when the box is open. When the box is open. But in the quantum world, when the box is closed, the entire system always maintains an uncertain wave state. That is the cat's life and death superposition at the same time. Before we observe it, the cat was dead and alive, and the wave function of that cat collapsed after the box was opened for observation, and the cat was either dead or alive. Now, since each experiment must produce a live cat and a dead cat at the same time, the universe split into two, one with a live cat, another with a dead cat. They exist in two parallel universes. Well, I said that in a few minutes only. It's very hard to understand. If you're a physics student, you want to understand this, perhaps you need to study a year for the quantum mechanics. But there's a video. I'm going to show this video to help me to explain that.
In quantum mechanics, if you know the quantum state of a particle, that is, its wave function, you can use the Schrödinger equation to calculate what that particle will do in the future. Usually, it spreads out over time as it is doing here. Note, to make this animation, we really solved the Schrödinger equation. Quantum mechanics, we never actually observe the wave function like this. Instead, when we measure it, we find the particle at a single point in space. At each point in space, the wave function has a complex amplitude, essentially just a real number plus an imaginary number. Max Born suggested if you take that amplitude and square it, you get the probability of finding the particle there. The fact that you have to square the amplitude probability was introduced into the core of our picture of reality. That's a pretty big philosophical leap. I mean, no longer is the universe deterministic. This made a lot of scientists, especially Einstein, uncomfortable. But the Born rule, as it is now called, remains at the heart of quantum mechanics because it is spectacularly successful at predicting the outcomes of experiments. Schrödinger's cat thought experiment. Put a cat in a box with a radioactive atom. Add a radiation detector that triggers the release of poisonous cyanide gas. The whole point of the experiment is to magnify the state of the atom up to the state of something macroscopic and tangible. He could have picked anything. It didn't have to be alive, but Schrödinger selected a cat. If the atom decays, the detector detects radiation, releases the poison, and the cat dies. If the atom doesn't decay, the detector doesn't detect radiation, poison is not released, and the cat remains alive. Since the state of the cat and detector apparatus are directly tied to the state of the atom, we say they are entangled. Where things get weird is that according to quantum mechanics, the state of the atom does not have to be either decayed or not decayed. Generally, it's in a superposition of both, decayed and not decayed at the same time, assuming no measurements have been made. This superposition state of the atom gets entangled with the detector, and then the cat. So after some time, the wave function of everything inside the box is in a superposition of the atom has not decayed, poison not released, cat alive state, and the atom has decayed, poison released, cat dead state. So according to quantum mechanics, the cat really is both alive and dead at the same time. Only when we open the box and make a measurement does the wave function collapse and the cat actually becomes either dead or alive. There, we have to examine the three essential components of Schrödinger's cat: superposition, entanglement, and measurement, to see if any of them is flawed. Superposition is the idea that quantum objects can be in two different states at the same time. This seems like a crazy idea and something we'd never observe, but we do indirectly with the double slit experiment. Fire individual electrons through two slits at a screen, and the pattern you see is not just the sum of electrons going separately through one slit and the other slit. It is an interference pattern. We are forced to conclude that a single electron somehow goes through one slit and the other slit simultaneously. This is superposition. Of course, it's easy to understand superposition with waves. They are spread out in space. And it's clear how the peak of a wave from one slit cancels with the trough of the wave from another slit to produce the interference pattern. And luckily we know that when we're not looking, electrons are represented by a wave, the wave function. The double slit experiment then is concrete evidence that this wave enables individual electrons to pass through both slits at the same time. So superposition is on solid ground. The next concept is entanglement. Consider two electrons fired toward each other with equal and opposite velocities. We know they will scatter off each other, but we don't know exactly how. Their trajectories are given by spread out wave functions that only give us probabilities. But as soon as we measure the momentum of one of the electrons, we immediately know the momentum of the other one. It must be equal and opposite, otherwise conservation of momentum would be violated. Now, this may seem obvious, but consider that before the measurement, the momentum of each electron was in a superposition of states. Measuring one instantaneously collapsed the wave function of the other. And this would be true even if those electrons were light years apart. These electrons are entangled. What's really going on here is that after interacting, the electrons do not have separate wave functions at all. They are described by a single wave function, and this is what it means to be entangled. This explains why measuring one immediately affects the state of the other one, because the single wave function has collapsed. In fact, if we were being rigorous, we'd have to say that there is only one wave function, the wave function of the entire universe, which includes absolutely everything. But in the case of isolated, unentangled quantum particles, we can reasonably talk about their individual wave functions. And then once they interact with something else, entanglement is the result. So what we've seen is superposition is really the same thing as describing systems with waves. And entanglement means that after particles interact, they are described by a single wave function. These are fundamental parts of quantum theory, describing systems with wave functions that evolve according to the Schrödinger equation, which leaves only measurement. But doesn't it seem weird that there should be one rule for how systems evolve when we're not looking, and a different rule for when we are? So what if we throw out all the rules associated with measurement? Well then, in the Schrödinger's cat thought experiment, the radioactive atom in a superposition of decayed and not decayed gets entangled with the detector and in turn the cat. Now remember, we are also made of electrons and atoms which obey the laws of quantum mechanics, so we are quantum mechanical too. So when we open the box, there is no measurement, no wave function collapse. We simply get entangled with the state of everything inside the box. So we see the cat alive, and we see the cat dead. Now, how is that possible? I'm guessing you've never seen both an alive and dead cat before. But the solution is, it's because the you that saw the cat alive and the you that saw it dead actually inhabit separate worlds. By that I mean, they exist in their own complete realities, and those realities will never interact. But where did these separate worlds come from? Well, something I haven't mentioned yet are all the particles of the environment, the air molecules, photons, everything that we are not keeping track of. If a quantum object in a superposition gets entangled with the environment, it is said to undergo environmental decoherence. This branches the wave function of the universe, essentially splitting the universe into two slightly different copies. So, a more realistic account of Schrödinger's cat goes like this. The radioactive atom evolves from 100% not decayed into a quantum superposition of decayed and not decayed. The detector becomes entangled with this superposition state of the atom. But the detector is being bombarded by all these air molecules and photons in the box, which would bounce off differently if it is detected radiation than if it hasn't. So almost immediately, the detector becomes entangled with the state of the environment. It decoheres, branching the wave function in two. At that moment, you are split into two identical copies, one entangled with each outcome of the experiment. You continue to be identical until you open the box, but in this case, the cat actually is alive or dead. You were just finding out by opening the box. What we are unaware of is that the other outcome also happened, just to someone who is not you anymore. I mean, both observers came from you, but they are no longer you, and they are no longer identical to each other. Creating infinite, subtly different worlds all the time may sound implausible, to put it mildly, but consider that all those worlds are naturally part of the mathematics of quantum mechanics. Many worlds just takes them seriously. The wave function is the complete picture of reality, and our measurement is just a tiny fraction of it, the part we become entangled with when we interact with a quantum object in a superposition. The universe also goes back to being deterministic. Every outcome happens 100% of the time. It only doesn't look that way to us because we only experience our tiny sliver of the multiverse.
Okay, so this is expand parallel universes. We probably living in one of the parallel universes. We didn't notice the other universes because we are trapped in one of the universes. Now, at the end of this video, it mentioned the multiverse. So let me explain what is the multiverse. Okay, what exactly is the multiverse? The multiverse actually is a collection of parallel universes. Multiverse theory states there are multiple versions of the universe. Each is different with each other. Now, there's also famous collection of movie was played on the PBS. And so I cut a section of the movie, I showed it here, which just explains the multiverse.
The laws of physics as we experience them are set in the very earliest stages of the universe. And quantum fluctuations in everything would be responsible for another universe having slightly different laws of physics than ours. Because the quantum fluctuations will take it in a slightly different law of physics direction than our universe. And this would just keep going. Every universe that's born, even if it started out sort of the same in the very first instant, a later instant when other laws of physics manifest could be slightly different. With the multiverse, where there could be pockets of the universe that are expanding with no knowledge of any other pockets of the universe. These are essentially independent universes from one another, and never the twain will meet. Imagine you're a ship at sea and you look to the horizon, and that's your whole universe there, to the horizon. There's another ship that has its own horizon, and these ships don't even see each other. You'll only see each other if somehow your two horizons can overlap. And we don't know how to do that in our universe because they're non-causal. You'd have to find some way to tunnel from one universe to the other in order to access that, but that could be very dangerous. Because if the laws of physics are different than the ones you evolved on, then you could just dissolve into a pile of goo because the charge on the electron is different and all of your biochemistry would change. There could be a universe where the laws of physics there will never allow matter to coalesce. You'll never get stars. That would be a lifeless universe. There could be another universe where you can make stars, but you don't make heavy elements. That would be a universe with stars, beautiful night skies as we have now, but nothing that we know and love. No planets, no life. In the 1920s, quantum mechanics was invented, discovered, however you want to think scientific advances take place. Quantum mechanics is the study of the small, how particles behave. And we learned that if you get to a small enough scale, you lose the ability to predict with precision the behavior of the system. And you can only describe it statistically. And there are ranges of things it can do, and all you can describe is the range of properties that it may have. Well, here's this big grand universe we have described by Einstein's general theory of relativity. But at the Big Bang, the entire universe was the size of an atom. And so you have the need to have the physics of the small, quantum mechanics, marry the physics of the large, general relativity, because they're occupying the same space. Now, when you take quantum mechanics and apply it to aspects of the fabric of space on that scale, what you have is a gurgling of the fabric of space-time. In fact, it's been called a quantum foam. And so now, when you look at this foam, applying the laws of quantum mechanics to it, you realize that this fabric is not limited to one zone or another. In fact, there's a region of the fabric that could hatch out an entire universe with the variations in the laws of physics simply because the conditions that would spawn the laws of physics had variation in them. And so the multiverse is not just some invention out of the ether. It flows out of an application of quantum mechanics to general relativity.
Okay, so there's a multiverse. Now, this picture I show on the screen is, you can see it maybe in the physics textbook, or maybe in the magazine. It shows, okay, our universe is just one of the universes, there's a multiverse. But I can tell you this picture is wrong. Why? Because this picture shows us the three-dimensional aspect of the multiverse. This is because to human, we are trapped in the 3 dimension and we can only imagine 3-dimensional object. But through the mathematics, you understand the multiverse we are talking about here is not only 3 dimension, it's a higher dimensional concept. Now to illustrate and why this picture is wrong, maybe there's another example, another cross section to help us understand is the following videos. Let's imagine we are leaving the Earth, we fly towards the edge of the universe, we can escape from our universe. Let's see what happens. Okay, let's fly into another direction. Let's fly into the small. Okay, so this video is just an illustration, but actually it's not exactly correct. Why? Because for us, we can only see 3-dimensional pictures. Actually, we are essentially trapped in these 3 dimensions. We cannot go out of the universe because it takes the time longer than our lifetime, and we cannot go to the small world because we are trapped in these 3 dimensions. So before I conclude today, the very last story I want to talk about is we are part of the universe. Now let's look at and our nerve system, which is the inside our brain, and also the system of galaxies. You see on the top is our nerve system, on the bottom is galaxy. What's the difference? One of the differences is the time scales. Our lifetime is 100 years, let's say. The time needed I travel across my space is 1 second. However, the time needed to travel across the galaxy is 100,000 years. The galaxy is 1 second. So that's why the lifetime of galaxy is so long. But both nerve and galaxy systems are arranged in well-defined networks with nodes and neurons in the brain and galaxies in the universe. They're connected via filaments. You can imagine, hey, maybe there's a gigantic structures alive. They're connected with the system of galaxies. Now, this is the scale of space. How about scales of time? I mentioned this as a cosmic calendar in my previous lectures. And compared to the entire universe, we are the last few seconds on the cosmic calendar. And universe has existed, our universe, 13.8 billions of years. Now, to think about that, well, and how about the life? Maybe we're already dead for 13.8 billion years. We only are alive for a few seconds. But this is our concept of time. Is the time the same as the space? The time in the future are connected with the time in the past? And physics says yes. Time is connected.
The beginning of the universe, the Big Bang, created all of space and all of time at once, in a big whole something. So every point in the past and every point in the future are just as real as the point of time you feel yourself in right now. Einstein believed that literally. One of his best friends died, and he wrote a letter to this person's wife, talking about how his friend still exists. Time is a landscape, and if you had the right perspective on the universe, you would see all of it laid out in front of you, all past, present, and future as a whole thing. And he said, your husband, my friend, is just over the next hill. He's still there. We can't see him where we are now, but we are on this landscape with him, and he still exists just as much as he ever has. Einstein believed that you right now have been dead for trillions of years, that you haven't been born yet, that everything that's happened to you, if you could get the right perspective on the universe, you could see all at once.
Presentism, the notion is that only the present is real. The past was real. The future, some configuration of the future universe will be real, but for now, only the present is real. In contrast, the opposing view is called eternalism. Eternalism, you have the past, present, and future are all equally real. So that makes the present just an arbitrary point in time, or an arbitrary moment in time. So one way to think about this is now is to time as here is to space. So in the same sense that I happen to be here and some viewers are out at some other point in space, and we're all comfortable with that notion that other points in space are equally real, in eternalism you have to be comfortable with the notion that other moments in time are as equally real as this moment in time, and this is just an arbitrary moment.
And so if a physicist comes to me and says, do some readjustment, face it, the future looks different from the past to you, but actually physics tells us it's the same, I at least acknowledge that I have an obligation to take that seriously, to listen to it. And physicists do argue about these things, and it's fair to argue about it.
So modern physics has required us to really let go of the idea of time as something that just flows.
Okay, so what we learned here is one thing in terms of space and time, no matter how big, how small you are, the universe is big, the quantum world is small, but we are all part of this universe. We are in this universe. And perhaps more important than both of these facts is that universe is also within us. So this is the final video I'm going to show, and about the birth is connected to the line and to the dance. Why? That's because we are part of this universe.
When you're in the way of waking up and finding out who you really are, what you do is what the whole universe is doing at the place you call here and now. You are something the whole universe is doing in the same way that a wave is something that the whole ocean is doing. The real you is not a puppet which life pushes around. The real deep down you is the whole universe. So then, when you die, you're not going to have to put up with everlasting non-existence, because that's not an experience. A lot of people are afraid that when they die, they're going to be locked up in a dark room forever. And sort of undergo that. But one of the most interesting things in the world, this is a yoga, this is a way of realization. Try and imagine what it will be like to go to sleep and never wake up. Think about that. Children think about it. It's one of the great wonders of life. What will it be like to go to sleep and never wake up? And if you think long enough about that, something will happen to you. You will find out, among other things, that it will pose the next question to you. What was it like to wake up after having never gone to sleep? That was when you were born. You see, you can't have an experience of nothing. Nature abhors a vacuum. So after you're dead, the only thing that can happen is the same experience, or the same sort of experience as when you were born. In other words, we all know very well that after people die, other people are born. And they're all you. Only you can only experience it one at a time. Everybody is I. You all know you're you. And wheresoever beings exist throughout all galaxies, it doesn't make any difference. You are all of them. And when they come into being, that's you coming into being. You know that very well. Only you don't have to remember the past. In the same way, you don't have to think about how you work your thyroid gland or whatever else it is in your organism. You don't have to know how to shine the sun. You just do it. Like you breathe. Doesn't it really astonish you that you are this fantastically complex thing? And that you're doing all of this and you never had any education in how to do it?
Okay, I'm close to the end of the seminar now. Still, I understand many people feel, well, many concepts are very hard to understand, are very hard to grasp. This is why we need to study mathematics and science. People in love with mathematics and science. If you do, feel special. You are the one in many chosen by the universe to understand it deeply. And you are the one to discover its magnificent secrets. Thank you very much.
Thank you, Dr. Johnson. Wow, this is just so amazing. I have a lot to say, but I will leave the time for our student, lovely student. Yes, because we have a Q&A session. Before our Q&A session, as usual, I would like to call for the donation for our both host and the co-host two lovely nonprofit organization, AEC and CSAC. And if you are willing to support our student clubs or our student scholarship, you can contact below emails here to support our next generation, those young, I can say younger scientists, to live the human, to live us lead us to go to another maybe multiple universe. Who knows, right? Someday maybe we can reach out there.
Yeah,
Yeah,
you're
thank
right,
you.
yes.
Thank you, Dr. Johnson. Yeah. You can contact the email here, aecnonprofit@gmail.com. If you want to sponsor, make a scholarship for students, you can contact the guochengxi@gmail.com here. Yeah, thank you. Okay, so I believe there are a lot of questions in our lovely student here. So just as usual, if you have any questions you want to ask, just raise your hand and unmute yourself. Our host will invite you to the panelist and you can just feel free to ask, okay? Let me see.
Okay, you can ask any questions you may have.
Yes. So let me see. Is there any hand here? For the sake of the time, so we will have 3 questions here, okay?
Okay, 3
Okay,
questions.
Avery. Yeah, Avery, here you go. Oh, I saw 3 hands here. Okay, Avery first, okay? You can unmute yourself. And open your camera, yeah, if you would like. Where's Avery? So, Zhenhan, could you please invite Avery into the panelist? Thank you.
Or maybe we can move to the next question.
Oh, okay. So, how about Nathan? Let me. Either Zhenhan or Avery, you can go ahead to ask your question. Okay, Avery is here.
Oh, okay. I think I'm a panelist now. So my question kind of has to regard with like wormholes and black holes and their difference. So we say that we can theoretically like tunnel from one universe to another with these wormholes, right? And we're saying that's dangerous because like the difference in laws of physics and how these universes all develop independently. But does this but we also say that inside of a black hole, there's a possibility of there being another universe. So with a black hole, like with a wormhole, could you theoretically make contact with a universe inside of a black hole?
It's okay. And the wormhole and black hole concept is you go to the wormhole, you come back to the same universes. Okay, that's the concept for space travel in the future, which I'm going to cover and in the future lectures here. Okay, now if whether or not you need to go to another universes, this is mathematically possible, but whether or not you can be still alive in another universes, and this is not true because another universes may not have the same laws of physics and may have the different laws of physics. That's it, and maybe have a different chemistry and different biology. Okay, whether or not you can survive, and we don't know yet. Okay, but at least this is a mathematical concept which is possible. Of course, this is it's very, very frontiers, so if the physics student would love to explore it, and of course you can do it. Yeah.
Thank you.
Yeah. Thank you.
And
thank you, Jonathan.
Yeah. Okay. Maybe Nathan. I can see your hand.
Yes, Nathan.
Yeah. So I had a question about the quantum foam concept. So like I know this is like the theory where particles of matter and antimatter are like constantly created and destroy themselves. But doesn't this like release energy, and doesn't that violate energy conservation?
And it's not constantly appear and destroy. the antimatter and can be made in the experiment. Okay, and in the accelerator experiment. Okay, if you are being a very high energy, but so far so we cannot create stable antimatters. Okay, and so which is unstable right now. Okay, so again, this is another frontiers of research to see in the future if we can create antimatter and trap perhaps in the magnetic field and to make future use.
All right, thank you.
Yeah.
Great. Okay, so next one, Danny. This will be the last question. Oh, it's Eric. Okay.
Yeah. Okay, so I guess my question is like, for like story 3, Dr. Jonathan, you talked about like how it's possible to travel faster than light. Well, technically it's not possible. We're all moving at the speed of light, but then it's possible that the image or resolution moves just as fast or faster than the speed of light. So how can we use that in order to like travel faster in order to get to all of those places in space we can get to?
Yeah. The answer is in the 3-dimensional universe, and if you have a mass, okay, you cannot travel even at light speed, okay, and which is although the image and maybe shadows is moving faster than the light, but anything with the mass you cannot travel faster than light in our 3-dimensional universe. And if you want to overcome this, you need to, I think Eric just mentioned the wormhole, black hole. That's the possibility in the future, I should say. Yeah. Okay.
Yeah. Thank you. Thank you.
Thank you, Eric.
Okay.
Thank you, Dr. Johnson. Yeah. So for the sake of time, this is our last question. But don't worry. So the student, like in our intern, if you have questions, and we have our Skype group, so you can keep it and send the question to our Skype group and to have a discuss with Dr. Johnson. Okay. Okay. Thank you, everyone. Thank you for today's participation. Yes, we have a next seminars like announcement. Yeah. So for all the audience here, do remember that our next seminar will be scheduled on February 11th at the same time, and the topic will be Case Under the Stars. Hope to see you there and see you next month. Thank you.
Bye. Thank you.
Hi, Dr. Zhang.